What is a cirque? Is it A, circles in polar deserts formed by stones of different sizes? B, moraines at the end of glaciers that are curved? Or is it C, depressions in mountainsides where snow accumulates to form glaciers? The answer is C, depressions in mountainsides where snow accumulates to form glaciers.
In the last episode, we learned about the landscapes of the Arctic and the landforming processes, and we saw that permafrost was one of the features that controls the land. And just as an introduction to this episode, here you see one of many, many examples of how permafrost creates a very, very spectacular landscape in the Arctic. This is patterned ground, ice wedge polygons. Permafrost, what is it? Well, permafrost is ground that remains frozen for 2 more years. It is beneath about 20 to 25% of all the land masses in the Northern Hemisphere. So it's very important. It occurs from the north of the Arctic, where it's continuous. Wherever you dig in the ground, you'll come across permafrost, basically, all the way to the southern limit of permafrost, where it gradually breaks up from being continuous. It becomes discontinuous, sporadic, and then isolated. The thickest permafrost in the world is about 1.5 kilometers thick. It is very substantial. And the oldest permafrost is about 3 million years old. It's also found on the continental shelves. And you can see this green hatching here off the coast of Siberia. There's permafrost there too. But that's outside the scope of this series, even though it's extremely important permafrost. But I want to reassure you that permafrost is not a substance, it's not soil or bedrock, it's everything that it remains frozen for more than 2 years. As I mentioned, it creates many, many features, all the way from the mountains where you can see rock falls, active layer detachment where the soil just slides off the permafrost, to thaw lakes where the permafrost has thawed and a depression has opened up and water accumulates, and then the polygonal tundra, the ice wedge polygonal tundra that you saw in the first opening slide. So it has a very big impact on the way the environment looks. And just to reconfirm that, here are some rock cracks where there's been permafrost in rocks, and that has opened up movement and dynamics in the rock face. You see pingos, these are hills, quite large hills that are created by ice coming together, aggregating in the permafrost area and pushing the ground up. Other examples you've already seen, the ice wedge polygons. Here you see a dynamic where some of the polygon centers are sinking, getting wet, and creating ponds. And then on the right, you see what happens when some of that permafrost, some of the ice wedges thaw, and you see a bridge of the active layer over where there was ice, where there was permafrost. Other examples, pulsars. Pulsars are peat mounds, individual mounds with permafrost inside a frozen core, and when they start to thaw out and break up as it gets warmer, they create these small thaw lakes. In other examples, the thaw slump is where the active layer just completely detached from the whole area and slides into downhill or into a lake. So let's look now at what happens in the dynamics of permafrost in a normal situation when we don't have climate change. The animation shows you the surface of the tundra with shrubs and grasses and mosses in the depressions and lichens on the little hummocks. And below that we have the active layer. You'll see the active layer is greater than 0 degrees C in late summer. It's thawed out. Below that it can be soil, it can be bedrock, it can be various materials, but there we have the permafrost, which is less than 0 degrees C, is frozen. And in that you see little white shapes. These are ice lenses within that permafrost, and they vary in their size and their distribution. And below that, we have the unfrozen bedrock, which goes all the way down. As we go into autumn, early winter, something different happens in the Arctic than elsewhere. In many places, you have what we call two-sided freezing. So it gets cold on the surface as the weather gets colder, and also the permafrost surface, the active layer just above that freezes too. So the active layer is squeezed between these two freezing fronts, and you can see the vegetation starting to change into its autumn colours. As we go into late winter, then of course we have the snow. By this time, all the active layer is frozen. And below that, of course, we have the permafrost and then the unfrozen bedrock. I would also say that as the whole of the active layer freezes, that also produces some features that are important in ecology. There is a displacement of the surface. There is upward heave. We call it frost heave. And as a result of that frost heave, we can have cracks in the surface developing. And very often, young seedlings of plants are literally thrown out of the ground because of this freeze-thaw process. And this is one of the limitations to agriculture in the north. When we go into the next early summer, then we come to the thaw period, and now the shrubs are producing their buds, the snow is disappearing, the surface is wet, and the top of the active layer is thawed out. But still, the base of the active layer is thawing, and the thaw front is going down, but it will stop at the permafrost table. If we now look at the situation in a warming climate, then what we see is increased grass growth, increased shrub growth. We see at the surface of the permafrost, where the permafrost meets the active layer, that some of the ice lenses have actually thawed, and there you see wet soil. But that has led to a little bit of subsidence, so you now see the topography of the surface changing a little bit more, with the depressions being slightly bigger depressions and the hummocks being slightly higher hummocks. And eventually we go to a situation where those depressions get very big, or much bigger, and water accumulates, and we have now a thermokarst pond, or a thaw pond. And also the vegetation is changing, because now we have open water, so we have sedges like the cotton grass. The shrubs are growing because it's a warmer climate. And look at the permafrost. The permafrost now, it's not everywhere. It's isolated into a small patch, and that patch is very, very thin. And the permafrost has basically been reduced while the active layer has grown. If we want to know what is happening to our permafrost now, then there are two ways of doing that basically. One is to take a drilling rig into the Arctic, which is not trivial, to drill a borehole and to measure temperature in that borehole for tens of years. Another way, as in the other photo, is to get an implement that you can press through the active layer until you hit the permafrost level. And then by measuring how the active layer grows in thickness, that tells you about how the permafrost is receding down the profile. And the graphic at the bottom just simply shows temperatures measured in boreholes round the Arctic, from very cold permafrost at -16 to some quite warm permafrost. And what you can see is that much of our permafrost is warming, and in some areas the permafrost is disappearing. What happens when permafrost disappears? Well, if that permafrost area is rich in ice, then you have subsidence. When you have subsidence, there are major impacts for infrastructures. Houses fall down, roads break up, airstrips break up, oil pipelines break, if they're not properly engineered. To properly engineer them, as in this case from a Russian settlement on Svalbard, there the houses have been insulated from the ground below so that heat from the houses does not affect the permafrost, but all this has economic costs associated with it. In the natural system, the subsidence, of course, leads to trees falling over. This is called the drunken forest, because the subsidence leads to trees just falling over. The permafrost also affects hydrology. That's the way the water flows. And you saw the example from the animation of how a pond is created. Here is another example. What you see in the middle, this dry track going up, is the edge of some polder, but the polder is degraded, and as the permafrost is thawing and creating that wet area to the right and to the left. You see the white flowers, the cotton grass, you saw those in the animation too. The thawing permafrost also affects land-atmosphere links, and I already mentioned in the very first introduction to the course about how permafrost protects carbon that was captured thousands of years ago. And when the permafrost thaws, that carbon is released to act as a greenhouse gas or a pollutant of ice, altering the albedo of ice and snow. And here is one example, which is, to my knowledge, is the most extreme example, which is from the New Siberian Islands, where the rate of coastal erosion is about 40 meters a year. And here you see carbon blowing off when it's dry weather onto the sea ice. You see carbon going as a gas into the atmosphere, and you also see that in the rain, it's going down into the streams and flowing out to the Arctic Ocean. At least three different major ways that carbon is being lost from the safety of being stored in permafrost. Permafrost, to some extent, is protected by peat in the subarctic lowlands because the peat insulates it from warm summer temperatures, but permafrost is also insulated by snow against low winter temperatures. So as the snow cover increases, so the permafrost thaw rate increases too. And here you see a very simple experiment with snow fences that trap snow on one side and deplete snow on the other side. Where you have the accumulation of snow, the permafrost thaws faster there than where there is less snow.
Is permafrost A, permanently frozen water, B, permanently frozen soil, C, permanently frozen sediment, D, permanently frozen rock, E, all of the above, or F, none of the above?